Right, so since last time, okay, welcome back. Thank you for being here. Last time Jan was using the tablet, right? And how can Jan use the tablet and I don't use the tablet, right? So I should be as cool as Jan at least, I think. One more thing to begin with. There is a spreadsheet where you can decide whether you'd like to join the Slack channel where we collaborate over making like some drawings for the website, fixing some mathematical notations, having some kind of, fixing the error in English, in the English grammar or whatever. So if you're interested in helping improving the content of this class, feel free to fill up the spreadsheet, okay? We are already a few of us on the Slack channel, so, I mean, if you want to join, you're welcome. So instead of writing on the whiteboard, because it's impossible to see, I think from the upper side, we're going to I'm going to experiment with a new toy here. All right. First time, so, I'm a little bit tense. Last time I screwed up with a notebook, so, okay. All right, so we are going to be starting with a small review about linear algebra. I hope I'm not offending anyone. I'm aware that you already taken linear algebra and you're very strong in it, but nevertheless, I'd like to provide you my intuition, my perspective, okay? It's just, one slide, not too much. So maybe you'd like to take out some paper and a pen, or you can just, whatever, follow along. So this one is going to be linear algebra review. Okay? Am I waiting a little bit? Okay, let me wait for a sec. Ready? Yes? No? Shake your head? Okay, fantastic. All right, so we were talking last time. We had a neural network with an input on the bottom, then we had like an affine transformation, then we have a hidden layer, right? So I'm going to just write the first equation. We're going to have that my hidden layer, and since I'm writing on with a pen, can you see anything? Yeah. So since I'm writing with a pen, I'm going to be putting an underscore underneath the variable in order to indicate it's a vector, okay? That's how I write vectors. So my h is going to be a nonlinear function f applied to my z. And z is going to be my linear input, okay? The output of the affine transformation. So in this case, I'm going to be writing here z is going to be equal to my matrix A times x, okay? We can imagine there is no bias in this case. It's generic enough because we can include the bias inside the matrix and have the first item of the x equal to be 1. So if this x here belongs to Rn, and this z here belongs to Rm, first question, what is the size of this matrix? Okay, fantastic, right? So this matrix here is going to be a m times n. You have as many rows as the dimension where you shoot to, and you have as many columns, the dimension where you're shooting from, okay? All right, so let's expand this one, right? So this matrix here is going to be equal to what? You have A11, A12, so on until the last one, which is going to be, shout? 1n. Thank you. 1? N, yeah. 1n. Then you have second one is going to have 1a to 1, a to 2, so on until the last one, which is 2n, right? And then you keep going down until the last one, which is going to be, what are the indexes? M1, right? Okay. So you have a M1, a M2, and so on until Mn. Okay, thank you. All right. And then we have here our x, right? So you're going to have x1, x2, and so on until xn, right? You're more responsive than last year. Good. Thank you. All right, so we can also rewrite this one in different ways. So the first way I'm going to write this one is going to be the following. So I'm going to have here this A1 Then I'm going to have here my A2. And then I have the last one, which is going to be my AM. Okay? And then here I'm going to be multiplying this by a column vector, right? So my column vector, I'm going to be writing like this. All right, so what is the output of this operation? So this is a matrix, you have a vector, the outcome is going to be a vector. So what is going to be the first item of my vector? I don't use dots because I'm not a physicist. Actually, I am, but we are doing linear algebra. So what should I write? All right, so that's already transposed because those are row vectors. So I just write A. I'm going to just write, right? So I have A1 X, okay? So there is no transposition here, no dots around, and so on. Second element is going to be A2, okay? X, and then until the last one, which is going to be the... Okay, there is no dot, but sure. Like someone is calling that dot product instead of the cross product, but that is assumed like you use a different kind of notation. All right, so, and this is going to be my, so how many elements does this vector have? M, okay, so we have Z1, Z2, and so on until Zm. And this is my final Z, right? My vector Z. Okay, fantastic. So now we are going to be focusing a little bit about the meaning of this thing over here, okay? Are there questions so far? No, right? It's very trivial so far, I hope. I mean, let me know if it's not, okay? Okay, so let's analyze one of these guys here. So I'd like to figure out what is the meaning of writing AT times X, right? So my AT is going to be my generic AI. So let's assume in this case when n equal 2, okay? So what is ATX? So ATX is going to be equal to what? So let me draw here something so that is going to be easier for you to understand. So this one is going to be my A. This is going to be my alpha. And then here you have like, this is going to be my X. And this is going to be here my Xi. So what is this? What is the output of this product here? This one here.
Is it a column vector or a row vector?
Say again, sorry?
Isn't A a row vector?
A transpose, let's call it, let's have that as a row vector. Can you see? No? What is going to be the output of this operation here?
So is M also equals to 2?
No. Why?
So it can be arbitrary, right?
This is like a generic one of the many A's, right? There are M A's. This is one of those M A's. So I'm multiplying one of those A's times my X, right? Let's assume there are only 2 dimensions. So what is going to be the output of this scalar product? Can someone tell me?
Magnitude of A times
No. Like normal scalar product.
It represents, for example, if X was in 2D space, then where would first basis vector lie?
Hold on. So you have A here. Then you have here, this part here is going to be A1. And this is going to be A2, okay? Then you have here X1, and then you have X2, right? So how do you express this scalar product here? Okay, so I'm just writing. Let me know if it's clear. So I'm going to write here A1 times X1 plus A2 times X2, right? This is the definition. Clear, right, so far? Yeah, no? Okay. Yeah, question?
Is the T meant to be a transpose?
Yeah, the T is meant to be a transpose. It's a row times column vector. So let's assume A is a column vector, then I have row times column, right? So let's keep writing this stuff here. So what is A1? how can I compute A1? Say again? Okay. So I'm going to write here, the A1 is going to be the length of vector A times cosine alpha. Then what about x1? Someone else? The same, right? No, wait, what?
No.
What is x1?
Same thing.
Same thing, right? Different letters. So someone say something? You're following, you're completely confused, you're not having any idea, it's too easy, I have no idea what's going on here. It's good, right, so far? Okay, what's going to be the second term?
Mod x cos
This one is going to be x here, right?
Yeah.
Times cos xi, right? And then you have the second term, which is going to be what? Magnitude of A. Shout, I can't hear.
Sine.
Okay, sine of alpha, then
magnitude of x
okay, thank you.
sine.
Okay. All right, I'm going to be just putting together those two guys. So you're going to get equal magnitude of A times magnitude of x times cosine alpha cosine xi plus sine alpha and sine cosine sine xi. Sorry. What is the stuff in the parentheses?
Cos of psi minus alpha.
All right, so there's the cosine of the difference of the two angles, right? Everyone knows trigonometry here, right? It's high school stuff. So this one is going to be equal A x times the cosine of xi minus alpha, right? Or the other way around, alpha minus xi. So what does this mean? You can think about each element. So far it's clear, right? I didn't do any magic. Yeah, shake your head like this for yes, this for no, this for maybe. No, I'm joking. Okay, so you can think about whenever you multiply a matrix times a vector, that basically each output of this operation is going to be measuring. So, okay, hold on. What is this cosine? How much is cosine of 0? 1. So it means if these two angles, if the two vectors are aligned, which means there is a 0 angle between the two vectors, you're going to have the maximum value of this element, right? When do you have the minus, the most negative value? When they are opposite, right? So when they are in oppositional phase, you're going to get the most negative magnitude. But then if you apply just, let's say, a ReLU, you're going to cut all those negative things, and you're just checking for the positive matches, right? So neural net basically just perhaps is going to be figuring out only the positive matches, right? And so again, when you multiply a matrix times a column, a vector, you're going to be performing scalar product between each column, each row of the matrix, which represents your kernel, right? So whenever you have like a linear layer, your kernel is going to be the whole row of the matrix. And then you see what is the projection of that input on that column. On the input on that row, right? So each element of this product is going to tell you the alignment with which the input is, what is the alignment of the input with respect to the specific row of the matrix, okay? Yes? No? This should shade some more like intuition while we are using these linear transformations. They are like allowing you to see the projection of the input onto different kind of orientations, let's say this way. Okay?
Can you prove this for high dimensions?
You can try to, extrapolate this in high dimensions. I guess the intuition, at least I can give it to you, works definitely in 2 and 3 dimensions. In higher dimensions, I kind of think it works in a similar way. Next lesson, we are going to see what is the distribution of the projections in higher dimensional spaces. This is going to be so cool, I think. All right, so this was the first part of the class. There is one more part. So actually here, this Z here, we can also write it in a different way. So maybe this is, maybe it's known, maybe it's not known. When I saw it first time, I didn't know. So, it's it's cool that sometimes you see these things once again, maybe. So let's go back here. It's the same z there. And so you can express this z as being equal the vector a1. And in this case, a1 is going to be the first column of the A matrix, okay? And this one is going to be multiplied by the scalar x1. Now you have the second column of the matrix, so you have a2. This is multiplied by the second element of the x, right? Until the last one, which is going to be... Say again? I can't hear if it's m or n. M, like this, or n? You know, sign language? Which one? N, right? You know sign language? No. You should learn. It's good. You know, inclusivity. an, right? So the last column times your xn, of course, because x has a size of n. There are n items, right? And so basically, when you do a linear transformation, or linear, apply a linear operator, you're going to be basically weighting each column of the matrix with the coefficient that is in a, you have first column times the first coefficient of the vector, second column by the second item, plus third column times the third item. And so you can see the output of this linear transformation is a weighted sum of the columns of the A matrix, okay? So this is a different kind of intuition. Sometimes you see this as like, whenever you want to express your signal, your data, is a combination of different decomposition. This is kind of a linear decomposition of your input. All right, so that was the first part. That is the recap about the linear algebra. Second part is going to be something even more cool, I think. Questions so far? No. Easy? Too easy? You're getting bored? Sorry. Okay. All right, then I'm going to speed up, I guess. All right, so let's see how we can extend the stuff we have seen right now to convolutions, right? So maybe convolutions sometimes are a little bit weird. Let's see how we can do an extension to convolutions. All right, so let's say I start with the same matrix. So I'm going to have here 4 rows and then 3 columns. Okay, so my data has to be if I have this matrix, if I multiply this to a column, my column vector should be of size 3. Thank you. All right, so let me draw here my column vector of size 3, right? And this one is going to give you a output of size 4. Okay, fantastic. But then, is your data, let's say you're going to listen to some nice audio file. Is your data just 3 sample long? How long is going to be your data? Let's say you're listening to a piece of music that is like 3 minutes. How many sample does 3 minutes of audio have?
Sampling rate.
Yeah, guess what is going to be my sampling rate?
44,000.
Let's say 22, okay. 22,000 kilohertz, right? 22 kilohertz. So how many samples 3 minutes of music have?
80 times 22,000.
Say again?
180 times 22,000.
You sure? Is it monophonic or stereophonic? Just kidding. Okay, so you're going to multiply the number of samples, the number of seconds, right? Number of seconds times the frame rate, right? The frequency in this case. Anyhow, so this signal is going to be very, very long, right? It's going to keep going down. So if I have a vector that is very, very long, I have to use a matrix which is going to be very, very fat, wide, right? Okay, fantastic. So this stuff keeps going in this direction. All right, so my question for you is going to be, what should I put in this location here? What should I put here? So, do we care about things that are further away? No. Why not? Because our data has the property of locality. Fantastic. So, what am I gonna be putting here? A big 0, right? Fantastic. Bam. Okay, so we put a 0 here, and then what is the other property? So let me start drawing this stuff again, right? So I'm going to have my kernel of size 3, and then here I have my data, which is going to be very long, right? So on. I can't draw, hold on. I can't see. All right, so here there are 0. Then let's say, what is the other property my natural data have? Stationarity, which means the pattern that you expect to find is going to be kind of repeating over and over again, right? And so if I have here my 3 values here, perhaps I'd like to reuse them over and over again, right? And so if these 3 values, let me change the color maybe so you can see there is the same stuff. So I have 3 values here, and then I'm going to be using these 3 same values one step further, right? And then I keep going further down, and I keep going this way. All right, so what should I put here on the bottom? What should I put here? A 0, right? Why that? Why is that? Because of locality of the data, right? So putting zeros around is called, it's also called padding, but in this case it's called sparsity, right? So this is like sparsity. And then the replication of this thing that is over and over again is called stationarity. Was the property of the signal. This is called weight sharing, yeah? Okay, fantastic. All right, so how many values do we have now? How many parameters I have on the right-hand side? Wow, so we have 3 parameters. On the left-hand side instead we had 12, right? So is the right side is the right side going to work at all? You have 3 parameters on one side, on the other side you have 12. Okay, that is good using locality and whatever, no? Like sparsity and parameter sharing, but then now we end up with just 3 parameters. Isn't this too restrictive? How can we have multiple parameter? What's missing here in the big picture? There are multiple channels, right? So this is just one layer here. And then you have this stuff coming out from the board here. So you have the first kernel down here. Then you have some second kernel, let's say this one. And then you have last one here, right? And so you have each plane of these metrics being containing just one kernel, which is replicated multiple times. Who knows the name of these metrics? No, so this is going to be called Toeplitz matrix. Okay, so what is the main feature of this Toeplitz matrix? What is the big thing that you notice? It's a sparse matrix, okay? Okay. What is going to be here, this first item over here? What is the content of the first guy? Yeah?
Sorry, could you just repeat what each of the 4 figures are on top?
So this one here is going to be the extension of my linear transformation, which was, I have a signal that is longer than 3 samples. Therefore, I have to make these metrics fatter. Second part is going to be, given that I don't care about what things that are here down, I don't care about things that are here if I look at points that are up here. So I'm going to be putting a big 0 here, such that everything that is down here gets cleaned up, right? And then finally, I'm going to be using the same kernel over and over again because I assume that my data is stationary, and therefore I assume that similar patterns are going to be happening over and over again. Therefore, I'm going to be using this one, which is written here parameter sharing, weight sharing. Okay. Finally, given that this one gives you only 3 parameters to work with, I will use several layers in order to have different channels. So this one is one kernel. Before, one kernel was the whole row of the matrix. Okay. So when you have a fully connected layer, the only difference between a fully connected layer and a convolution is that you have the full damn row of the matrix. Okay. So what is going to be this first item over here? Anyone?
Was 3 inputs of the signal times the green kernel.
So the green kernel, let's call the green kernel just A1. Let me actually make it green, because it's green kernel. So you have A1 times what? It's going to be from the number 1 to number 3, right? And then the second item is going to be same dude here, A1. And then you're going to have the x shifted by 1, and so on, right? Make sense?
More than one output. Like we also have the blue one with the green one.
Yeah, and then you're going to have, this one is going to be the green output, then you're going to have the blue output, one layer coming out, and then you have the further one, the red one coming, even one layer out. Okay? Was the iPad experience cool? Yes? No? I liked it. Okay. Other questions?
What that blue circle for?
Say again?
What that blue circle for?
The blue circle. This one?
Yeah.
It's a big 0. That's the sparsity one. The same as here. Yes? No? Yeah. Yeah?
So for those like RGB or
Yeah, green.
those are the colors, but I don't quite get how to I'm trying to visualize what's happening there.
So here I just put a lot of zeros inside here. So I kill all the values that are away from the little part. And then I repeat the same 3 values over and over again, because I expect to find the same pattern in different regions of this is the big signal I have.
Yeah, but then under that, where you have the different colors.
This one here?
Yeah.
So I said that in this case I'm going to have just 3 values, right? And we started with 12 values and I ended up with 3, which is really, really little. So if I'd like to have, let's say, 6 values, then if I want to have 6 values, and I can have my second 3 on a different plane, and I perform the same operation. And whenever you multiply this matrix times a vector, you perform a convolution. So it's just to tell you that a convolution is just a matrix multiplication with a lot of zeros. That's it.
So in this case, it would actually be there's a green and a blue and a red stacked up.
Yeah, so they're going to have this one here, then you have a second one, then you have a third one. So you have 3 versions of the input.
Okay.
All right. So for the second part of the class, I'm going to be showing you some more interactive things. Please do participate to the second part as well. All right, so let's try. So I have rebranded the website, and now it has slightly some, the environment is going to be called PDL, so PyTorch Deep Learning, instead of Deep Learning Mini Course. It was too long. So let me start by running this one. So PyTorch Deep Learning. So we can do just conda activate PyTorch Deep Learning, and then let's open notebook, the Jupyter notebook. All right, so now we're going to be watching going over the listening to kernels. So I show you convolution on paper, on my tablet. Now I'm going to be making listening to convolutions, okay, such that you can really appreciate what these convolutions are. Here we set the new kernel, right, which is called PyTorch Deep Learning. So you're going to notice the same kind of, procedure if you update your system. All right, so in this case, we can read the top here. So let me hide the top here. All right, so given the assumption of locality, stationarity, and compositionality, we can reduce the amount of computation for a matrix vector multiplication by using a sparse because local Toeplitz matrix because stationary scheme. In this way, we can simply end up rediscovering the convolution operator, right? Moreover, we can also recall that a scalar product is simply a normalized cosine distance, which tells us the alignment of two vectors. More specifically, we compute the magnitude of the orthogonal projection of two vectors onto the other, and vice versa. So let's figure out now how all this can make sense by using our ears, okay? So I'm going to be importing a library that a professor here at NYU made. And here I'm going to be just loading my audio data, and I'm going to have that in my X. And then my sampling rate is going to be in the other variable. So here I just show you I'm going to have like 70,000 samples in this case, because I have a sampling rate of 22 kilohertz. And then my total time is going to be 3 seconds, okay? So 3 seconds times 22, you get what? So it's not 180, you were saying. Who was saying 180? It was 3, right?
Minutes. I'm sorry.
Oh, it was 3 minutes. Oh, you're right. This is 3 seconds. So you actually are correct. My bad. So this is 3 seconds. So times 22 kilohertz, you get roughly 70,000 samples. Here I'm going to be importing some libraries to show you something. And then I'm going to be showing you the first chart. So this is the audio signal I have imported right now. How does it look like? Wavy. Okay, cool. Can you tell me how it sounds? That was a good guess. The guess was, yeah, you can't tell exactly what's the content, right, from this diagram, because the amplitude of, like, the y-axis here is going to be showing you just the amplitude. Can I turn off the light? Is it okay? Or you're... You sure? Okay, thank you. I really dislike this light. Okay, good night. Oh, see how nice it is. Okay, cool. All right, so you can't tell anything here, right? You can't not tell what is the sound, right? So how can we figure out what is the sound inside here? So, for example, I can show you a transcript of the sound. And actually, let me actually force this in your head, right? So you're gonna have. Oh, hold on, didn't work. Okay, all right. So now we actually heard it. Okay, so now you can actually see ting ting tum tum. No, you can kind of imagine a little bit. But okay, so what notes did we play there? Like, how can I figure out what are the notes that they are inside? So I'm going to be showing this one. So since this is a bit brighter, I can see your faces. How many of you can not read this? Oh, ouch. Okay. So let me see if I can ask for some help. Let me see. Maybe someone can help us out here. Okay. Let's see. All right.
Hey, Alf.
Oh, hi, Alf.
How's it going?
Yeah, I'm fine. Thank you.
Nice class there.
Oh, thank you for the class. Nice sweater.
Oh, nice sweater too.
We have the same sweater. Can you help us out here? They don't know how to read. Oh, the connection. What the hell? They cannot read the score. Can you help us out, please?
All right, let me try to help you out.
Oh, thank you.
Let me switch the camera.
All right. So here we go. We can go live and hear first how it sounds. Everything. So it's gonna be like that. How cool is that? All right. So the first one is that. Thank you. It took 4 lessons for you to clap me. So now. This is very nice of you. Let's keep going. A flat, and then we have E flat, and then A flat. The difference between the first A flat and the other one in frequencies is that the first A, this one, A flat, is going to be twice the frequency as the other one down here. And instead, in the middle, we have the fifth. We're going to figure out what is the frequency of that. And then we're going to be going to
a B flat here. On the left-hand side, instead we have the accompaniment. And so we're going to have a flat and a E flat. And then B flat and E flat. So if we put all together, we're going to get this one. Right? Simple, no?
Yep, thank you.
Bye-bye.
Bye. Hi, okay. See, this took a whole damn day to prepare. I was so nervous before coming here. I didn't know if it actually would have worked. Both of them, tablet and this one. I'm so happy. Now I can actually go sleep later. Anyhow, so this was like the first part. You're going to have the first note. There is a A flat. Then you have a B flat, A flat, and B. So you have tam, tin, tam, pam. And the difference between the first pitch, tam, and pam, is 1 octave. Therefore, the first frequency is going to be twice the second frequency, okay? So whenever we're going to be observing the waveform, one sign will have shorter, like the half the period of the other one, right? Especially the A flat on top, is going to have a period which is half of the period of the A on the bottom one, right? So you have tam, pam, okay? If you go half of this one, you get tam, right? Okay. Okay, so how do we actually get these notes out from that from the waveform? Who can tell me how can I extract these pitches, these frequencies from the other signal? Any guess? Okay, a Fourier transform. I think it's a kind of a good guess. What does it happen if I perform now a Fourier transform of that signal? Anyone can actually answer me? You cannot raise your hand because I don't see. Just shout.
You'll see multiple peaks.
So if you basically perform the Fourier transform of the whole signal, you're going to hear brang, like the whole notes together. No, pam, tam, 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 brang, all together, right? But then you can't figure out which pitch is played where. Or when, actually, in this case, right?
You need to convolve it with a rolling window?
So we need kind of a Fourier transform which is localized. And so a localized Fourier transform in time or in space, depending on whatever domain you're using, it's called spectrogram, right? And so I'm going to be now printing for you the spectrogram of this. Sorry. I'm going to be printing here the spectrogram of this one here. And so here you can compare the two, right? On the first part here, on this side here, you're going to have this peak here at 1600, which is the pam. Actually, it's higher. Pam. There you go. And then you have the second one, which is this peak here. Pam, pam, pam. And then this one. Pam. You can see this peak, right? Can you see this peak? Yeah. Pam, pam. Okay? So these peaks are going to be the actual notes I play with the right hand. So let's actually put those together, and I'm going to have here the frequencies. So I have 1600, 1200, and 800. Can you see here? I have 1600 and 800. Why one is double of the other? Because they are 1 octave apart. So if this is ta, ta, this is going to be pam, okay? And this is a fifth, which is like also has a nice interval. So let me actually generate these signals here. And then I'm going to deconcatenate them all. So I'm going to be playing both these. The first one is actually the original audio. But it doesn't work. Hold on. Let me try again. Whereas if I play the second one, the concatenation. Yeah, sorry, it's a bit loud. I cannot even reduce the volume. Oh, I can reduce it here. Oh, too much. Okay, let me go again. All right? So this is just the concatenation of these 4 different pitches. So guess what we are going to be doing next? So how can I extract all the notes that I can hear in a specific given piece? So let's say you play a full score, and I'd like to know which pitch is played at what time.
Convolution.
Of what? So the answer was convolution, just for the recording. I'm asking convolution of what?
Of the spectrogram?
Not convolution of spectrogram. So you have convolution of your input signal with what? With some different kind of pitches, right? Which pitches would you pick?
Can you tell us what the
No, let's say you don't see the spectrum because let's say I just play any kind of piece of music. So I'd like to know all possible notes that are there. What would you do?
And what is the pitch?
You don't know. All pitches. How would you try that?
You convolve with each pitch value in the notes.
Right. So, and which are all the pitches you may want to use if I'm playing the piano? All the keys of the piano, right? So if I play a concerto with the piano, then I want to have like a piece of audio for each of those keys, and I'm going to be running convolutions of my whole piece with the all keys, right? And therefore you're going to see hits, which are the alignment or the cosine similarity, whenever you get basically the audio matching your specific kernel. So I'm going to be doing this, but with these specific tones I actually extracted here. So here I'm going to be showing you first how the two spectrograms look like. The left side is going to be the spectrogram of my actual signal, x of t. And on the right-hand side, I have just the spectrogram of this concatenation of my pitches. So here you can clearly see this. Ta, 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 ta. But then here is, first of all, what are these bars here, these vertical bars? You're following, right? I can't see you. You had to actually talk back. What are these red bars here, vertical bars? The horizontal one, I already told you, right? These are pa, 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 pa. And the vertical, what is it? Sampling issues, right? Transitions. So whenever you have the pa, pa, you actually have one waveform, and then the other one waveform has to stop. So it's no longer periodic. And whenever you do a Fourier transform of a non-periodic signal, you get, crap. That's why whenever you get the junction between the the jump here, you're going to have this spike. Because it's going to get basically, you can think about the jump as like having a very high frequency, right? Because it's like a delta, right? So you can actually get all the frequencies. That's why you get all the frequencies here. Boom. Okay? Makes sense, right? So far, kind of. All right, so this is the clean version, the I cannot even sing. And what is the left side here? Why is on the left-hand side all red down there?
The left hand.
Oh, okay, yes, you knew. So the left side, left hand, the chords are the one I show you on the bottom left side. Okay, so let me finish this class and then I'll let you go. So here I'm going to be showing you first all the kernels. You can tell now the red one is going to be the first chunk of my signal, the real one. And then you can see the first pitch is going to be has the same frequency. Can you see? So the pam has the same delta t, the same interval, the same period. Can you see? You cannot nod your head because again I don't see you. You have to answer me. Can you see or not? Yes. Okay, thank you, fantastic. And so this one, instead, the third one, you can see that it starts here, the period, and it finishes here. If you go up here, you're going to see exactly there were two of these guys, right? So that's why you can see, that's how you can see this is like twice the frequency of the one below. Finally, I'm going to be performing the convolution of these four kernels with my input signal. And this is how they look like, okay? So the first kernel has a high match in the first part of the score, so between 0 and 0.5 seconds. The second one starts just after the first one. Then you have the third one starting at 0.3, I guess, and then you have the last one starting at 0.6, okay? And so, guess what? I'm going to make you listen to convolutions now. Are you excited? Oh, okay, you're actually answering now. Good. All right, and so these are the outcomes. Let me lower a little the volumes, otherwise you complain. Yeah, I can't lower the... Okay. So the first one, let's try again. How cool is that? You just listen to convolutions. Okay, so basically this was almost it. I have one more slide because I felt like there was some confusion last time about what is the different dimensionality of different type of signals. So I'm really recommending to go and take the class of Joan Bruna, which is Math for Deep Learning, and I stole one of his small things he was teaching. I just put one slide here together for you. So the slide is the following. So, okay. So we have the input layer or the samples we provide into this network. And so usually, or last time I defined this, I have this curly X, which is going to be made of those Xi's, which are all my data samples, right? And so I usually have M data samples. So my I goes from M1 to M, okay? So is this clear? Is this notation clear? Because it's a bit more formal. I usually am less formal, but then somehow someone was feeling a little bit not comfortable, I think. So this one is just my input samples. But we can also see this one is this curly X, which is my input set, as the set of all these functions as Xi's, which are mapping my omega, capital Omega, which is my domain, to a RC, which are going to be basically my channels of that specific example. And so here I'm going to be mapping those lowercase omega to these Xi's of omega. So let's see how this is different, this from the previous notation. So I'm going to give you now 3 examples, and you should be able to tell now what is the dimensionality in these examples. So the first one, let's say I have like the one I show you right now, the time, just one piece of audio signal. So my omega is going to be just the samples, like sample number 1, sample number 2, like the index, right? So you have index 1, index 2, index until the 70,000 whatever we just saw right now, okay? And the last value is going to be the t, capital T, which is the number of seconds, divided by the delta t, which would be the 1 over the frequency. And this is going to be a subset of n, right? So this is a discrete number of samples. Because you have a computer, you always have discrete samples. So this is my input data. And then what about the image of this function? So when I ask what is the dimensionality of this type of signal, you should answer this is a one-dimensional signal because the power of this n here is 1, okay? So this is like a one-dimensional signal. Although it may have the total time and the one there it was a sampling interval. On the right-hand side, you have the number of channels. Can be 1 if you have a mono signal. You can have 2 if you have a stereophonic, so you have mono there. You have 2 for stereophonic. Or what is 5 plus 1? That's the Dolby, like 5.1. How cool. All right, so this is still a one-dimensional signal, which may have multiple channels. Nevertheless, it's still a one-dimensional signal because there is only one running variable there. Okay? Is it somehow better than last time? Yes? No? Better? Thank you. Let's say thanks to Joan. All right, second example. I have here my omega is going to be the Cartesian product of these 2 sets. The first set is going to be going from 1 to the height, and also this one is discrete. And the other one is going to be going from 1 to the width. So these are the actual pixels. And so this one is a 2-dimensional signal because I have 2 degrees of freedom in my domain. What are the possible channels we have? And so here possible channels that are very, very common are the following. So you can have a grayscale image, and therefore you only output one scalar value. Or you get the rainbow there, the color, and therefore you get like my x, which is a function of the coordinates omega 1, omega 2, which is going to be each point is represented by a vector of 3 components, which is going to be the r component of the point omega 1, omega 2, the g component at omega 1, omega 2, and the blue component at omega 1, omega 2. So again, you can all think about this as a big, big data point, or you can think about this as function mapping a low-dimensional domain, which is a 2-dimensional domain, to a 3-dimensional domain, right? Finally, the 20, who knows the name of the 20-channel image? Yeah, that's a hyperspectral image. It's very common to have a 20 bandwidth. Finally, Who can guess this one? If my domain is R4 times R4. What can it be?
Video?
No. Video is still discrete, right? This is R4. So it's not even computer. Who said something there? I heard. Yes, that's correct. So this is space-time. What is the second one? Yeah, which momentum has a special name? It's called forward momentum because it has a temporal information as well, right? And so what's going to be my possible image of the x function? Let's say it's c equal 1. What is it? Do you know? So this could be, for example, the Hamiltonian of the system, okay? And so this was like a bit more mathematical, introduction or mathematical precision. How do you say? Make it more precise the definition. So that was pretty much everything for today. Let me turn on the light, and I see you on next Monday. Thank you for being with me.